In the last two videos, I've talked about how we can find an equivalent, a combined resistance for the two cases where the resistors are either connected in parallel or in series. I'll now take a look at an example to see how we could use this formula. Suppose I have a battery, say of 1.5 volts. This battery is connected to a number of resistors. There is one resistor here, and the circuit branches off here. That's connected to two resistors in series, and in the other branch there is one resistor. Okay, and then the branches join again and continue back to the battery. So this is a circuit, slightly more complicated looking than before. So it looks like we have both resistors that are in parallel as well as resistors that are in series. Now this resistor, suppose this resistor has a resistance of 2 ohms. Let's say that this one has a resistor of 2 ohms as well. This one is 3 ohms. And this one is 4 ohms. Okay. So the problem I want to solve is to find the current in this wire, which I'll call current I, the current that goes through the battery, and the currents in the two separate branches. I'll call that call this I1, and the current here, which I'll call I2. So this is the problem I want to solve, to find all the currents in these three parts of the wires. Okay. Now, just to remind ourselves of what we can use, we have Ohm's law. We have Ohm's law, which is V equals to IR. We have the formula for resistors in series, and that goes something like the combined resistance is equal to R1 plus R2, or maybe more if there are more resistors. And then for resistors in parallel, we have 1 over the combined resistor, the resistance, is equal to 1 over each of the separate resistors, each of the separate resistances added together, if they're all in parallel. And if I have For example, we should not forget that we also have equations that we can use or for the voltages and the currents. So in the case of the currents, we have the relation between currents at the branch points. Basically, the idea is that all currents, the sum of all currents going towards a branch point must be equal to the sum of all currents coming out from the branch point, because there must be the same number of electrons going in as coming out. So with this understanding, we can say that I1 is the current going through the battery. So this current must have split into two parts as it goes, as it branches out into these parallel lines. The currents that I call I1 and I2, and when they join together again, you get back I. So this means that I must be equal to the sum of I1 and I2. Now I must be equal to the sum of I1 and I2, and this comes from what we can call the conservation of charges. So that's the current, and we do have something for voltage as well, if you want to use it, and that is that 1.5 volts is the EMF. It supplies the voltage to do work in going through all the resistors. So if you imagine 1 coulomb of charge going around once, the total work done after it's gone through all the resistance must be 1.5 joules. So the work done in going through the individual resistor will give us the voltage across those resistors. So let's say the voltage across this resistor is V1. Now the voltage across this resistor, let's say, is V2. Okay. When the current comes here, it splits into two. So the voltage across these two resistors would be the same as across these two, because the two branches are connected to the same 2 points. Okay, it's just that every second the charge that comes that arrives at this point will split into two parts. Okay, so if 1 coulomb comes here, it'll split into one part here and another part here. But the total work done on both parts, when they go through all the resistors and reach the opposite point, would be the V2, right? So that's what the V2 here means. If 1 coulomb of charge goes from that point to that point, regardless of how it splits up. So therefore, the overall voltage, which I call V, which is the work done on 1 unit of charge, must be equal to the total work done as that unit of charge goes through each part of the circuit. And those would be V1 and V2. So we have these are essentially all the equations that we can make use of. Now it usually it depends on the information given, whether we are given the currents or resistors or voltage or some combinations. Depends on the information given. If we want to know which are the equations we should start with, and it takes some exercises, some practice to know what is a good way to do it. So for now, let me just try something. Let me try and make use of these equations and see if it helps. Now, if I want to make use of well, I can't exactly make use of Ohm's law to find the current directly. I might as well start from that. If let's say I want to find this current using Ohm's law, I might say, right, that's I, okay, and V is the cell voltage. But what is R? There are so many possible resistors here. So the R that I need would really be the combined resistor. Okay, so the moment I try to use Ohm's law, I'll find that I don't have R. Okay, but that's fine. It just means that it leads us to the next thing to try, which is that we might want to try and find R, which is the combined resistance of all the resistors. So if you want to find combined resistance, then obviously we should make use of those two equations for series and parallel. Unfortunately, the resistors here are neither in series nor in parallel. They are sort of a mixture of both. For example, I can't say that resistor is in series with that, although they look like one coming after the other, because there's a branch point there. That makes things complicated. But I believe I can say that these resistors here, these two resistors are in series, right? Because in between there's no branching. So I think it will be safe to say that those two resistors are in series, and together, these two resistors together should be in parallel with this resistor. Okay, because this set and this resistor are connected to the same 2 points on the two sides, the same 2 branch points. So what we might have to do is we might have to break down the problem, meaning just focus on one small part of this group of resistor and try to use these equations bit by bit. So as a start, it's probably easier if I just look at those two. If I think of these as resistors in series, which they quite clearly are, I can start by finding the combined resistance of those two resistors. So let me try that. If I combine those resistors, what would I get? Okay, that's the 2 ohm resistor. That's the 4 ohm resistor here. If I want to find the combined resistance of the 2 and 3 ohms, what would this combined resistance be? Alright, I want to think of the 2 separate resistors here as one single resistor. Then I could use this formula for combining resistors in series, and this formula says that we just have to add them. So therefore, the combined resistance of these two is just 2 plus 3. So that would be 5. And this new diagram certainly looks simpler than the old one, a little bit. Alright, if only because I now have only 3 resistors instead of 1, 2, 3, 4. So from this, I can next try to use those equations again. Now there's still no resistors in series, but those two are in parallel, as we understand. So therefore, I can just focus on these two and apply this equation for resistors in parallel. So let's say the combined resistors of this part is R. Got it, R. Therefore, if I want to find R using this equation, I would do 1 over R is equal to 1 over 5 plus 1 over 4. Okay, if I add this up, I'll get I'll do 5 times 4 is 20, and 4 times 1 is 4 there, plus 5 times 1 there, which is 5 there. And therefore R is equal to 20 over 9 ohms. Okay, so this is my resistance. I'll write it down in mixed numbers. That would be 2 and 2 over 9. So this is the resistance. So therefore we have found the combined resistance of those two in parallel. So let me draw what I have now. I still have this resistor of 2 ohms, but in place of those two in parallel, you can think of this as a single resistor of 2 and 2 over 9 ohms. Okay, so it definitely gets simpler. Alright, this one I have 2 in parallel. That one, right, I finally have just these two resistances in series. Okay, now before I continue, let me point out something quite maybe a little bit unexpected. If you think of adding resistors in parallel, obviously when we add them, like when we do 2 plus 3 for those two resistors in series, we end up with 5, which is an answer that is bigger. Right? We end up with the result that the combined resistance is bigger than the two separate resistances, and that's kind of what we might imagine if we combine things. When you put two things together, we would assume that we would expect that it will get bigger. But take a look at this answer. This is the result. This is the resistance when we combine two resistances in parallel. Now these two resistances are 4 and 5. And turns out that when we do this calculation, the answer that we get is 2, is a bit more than 2, and is definitely smaller than either of the two starting resistors. So this is a good thing to know, which is that if you find the combined resistance for resistors that are in parallel, your answer would always be smaller than any one of the separate resistances. And there is a simple reason for that. It is because when the current comes into this parallel resistors, the current splits up so that each resistor takes less current. So therefore the current would experience less resistance than if all the current goes through any one of the individual resistor. So that's one way to think about it. Okay, in any case, we get this combined resistance, which is smaller than the separate resistors. So from here, the next step should be straightforward, because it is now quite obvious that this resistors that I have now, the two resistances, are in series. They come one after another. There's no more branching, no more parallel resistors. So to find the combined resistance, I can simply add the two using this formula for resistances in series. So therefore, let me write this out. Therefore, the final overall combined resistor can be obtained by simply adding those two to give 4 and 2 over 9 ohms. So we have finally found the combined resistance of this whole lot, all 4 resistors that we started off with. It was a little bit complicated. We had to do it in 1, 2, 3 steps, but as it turns out, we can do it by using this formulae for series and parallel resistors repeatedly. Now, once we arrive here, we can go back to the question. Now, the question, if you remember, was to find the currents in each part of the circuit, I1 and I2. Now, if you remember how I described combined resistors, I've explained that a combined resistance is the resistance of a single resistor that will give the same current as when you have all the separate resistances joined together. So in other words, using a resistor with this value, the current in this simple circuit should be the same as the I, the unknown I that I wanted to find. And it is easy to do it here. Because I've just run one resistor, I can use Ohm's law directly. So let me rearrange Ohm's law to make R the subject. So R is equal to V over I. And V is 1.5. I okay, let's see. I've mixed up the I and R. It's the I that I want to find. So I is equal to V over R. V is 1.5 and R is that one. 4 and 2 over 9. And the answer is the answer is 0.355 amperes. So we have found I. Now the next thing I like to do is to find the separate I1 and I2. And this means that we have to go back to the starting diagram. Let's see. Or maybe not. Maybe I shouldn't go back all the way to the starting diagram. Maybe I should go back to this diagram. Right? This one is a bit simpler, but it still have the two parallel branches. So that means that the current here would be the I1 and I2 that I want to find. And I we already found. Right, that was the I. So it's better to use this one than to use that one, or we can just use this one, but remember that the 2 and 3 combines to give 5. So in either case, and this is simpler anyway. So if I use this, now I know that current. So how can I find the separate currents? Now one way to do it would be to okay, we would usually have to use Ohm's law at some point. So if I start by thinking about Ohm's law, then in order to find a current through a resistor, I must know the resistance and the voltage. Now if you look at this I1, for example, I know the resistance. I know the resistance on this wire is 5. But I don't know the voltage across this resistor. I know that the cell is 1.5 volts, but that 1.5 volts is the sum of the voltage across both this resistor and this pair of parallel resistors. So I could start by, say, finding the voltage across here. Now if I want to find the voltage across here, see what I could do. I could okay, the voltage across here is the V2. Okay, so the voltage across here is V2, and that's the same as the voltage across here. That's V2. Okay, these are equivalent circuits in the sense that the voltage, in the sense that this is the combined resistance of those two. Now I can find the voltage V2 across here using Ohm's law because I know I know that I is 0.355. So this is 0.355 ampere going through this resistor, and this resistance is also known, right? We have found it just now, 2 and 2/9 of an ohm. So therefore, we can use Ohm's law to find the voltage. It's just V equals to IR. So I will just take that times that. I will take that times that. And if I do that, I will get see what I'll get. I will get 0.789 volts. So this is obtained by multiplying those two. This times this, okay, to give this. Okay, now that we have this, this voltage is also the same as the voltage across here and here. Alright, they're all the same as V2. If I now look at this picture again, I found the voltage across this parallel resistance. So the voltage for two resistors in parallel, the voltage across them are the same because they are both connected to the same 2 points. So therefore 0.789 volts would be the voltage across this 5 ohm resistor. So this means that I can now find I1. All I need is to use the Ohm's law again. So let me write this out. To find I1, try and write it down here. I1 would be equal to the V over R of this branch. So for this branch, the V is the V2 and R is the 5. So it's the V2 over 5. Now V2 we already know is 0.789 volts. Okay, so we have all the numbers that we need. And when you divide these two, the answer is 0.158. 0.158 ampere. Okay, so this gives us the current going through the first branch, which is also here. So what we have now is we have found that this is 0.158 of an ampere. So that's the current going through here. 0.158 of an ampere. And that current we have already found to be 0.355 of an ampere. 0.355 of an ampere. And now it remains to find the I2. To find I2, we can make use of this, which says that the sum of I1 and I2 is equal to I. So these two currents, they merge together to give you I. So therefore, I2 must simply be the 0.355 minus 0.158. Right, this must be I minus I1. I from there, and I1 from there. So just take this number minus this number, and we should get the answer. So I shall leave you to try that out.